Good morning, everyone. We are the Wonder Pets group from class group number 1 and number 5, and we are here to report about Unit 4 of the subject Fundamentals of Surveying. So here is an overview of our report. Unit 4 talks about traverse, traversing, traverse stations, traverse lines, types of compass surveys, summary of the procedure for adjusting a closed compass traverse, latitude and departure, balancing surveys, and computation of area topics.
Hello everyone, I am Lorenz Bermejo, and I will be discussing the first topic of Unit 4, which is traverse, traversing, traverse stations, and traverse lines. First is the traverse. A traverse is a series of connected lines whose lengths and directions are to be measured, and the process of surveying to find such measurements is known as traversing. In general, chains are used to measure length, and compass or theodolite are used to measure the direction of traverse lines. Frequently in surveying engineering and geodetic science, control points are setting or observing distance and direction. The control points throughout the control network may consist of monuments, benchmarks, vertical control, and etc. And there are mainly two types of traverse. First is the closed traverse, which either originates from a station and returns to the same station completing a circuit, or runs between two known stations. And the second is the open traverse, which neither returns to its starting position nor closes on any other known station. Now let's move on to traversing. Now traversing is performed by 4 different methods, and these methods are classified according to the survey instrument used. The 4 methods are chain traversing, compass traversing, theodolite traversing, and plane table traversing. Chain traversing is done by taking linear measurements only. Hence, chain or tape is enough for chain traversing. The angle between the adjacent traverse lines is measured using the chain angles concept. Chain traversing is performed in areas such as ponds, etc., where it is difficult to adopt triangulation. In the case of compass traversing, both linear and angular measurements of traverse lines are taken by using chain and prismatic compass respectively. Both forebearing and back bearings are measured and required corrections for local attraction are applied. In the case of theodolite traversing, the linear measurements are done by using chain or stadium method, and angular measurements are done by theodolite. Using the theodolite, the magnetic bearing of the first traverse line is measured, and from that magnetic bearing of other sides are calculated. This method is very accurate compared to other methods. In the case of plane table traversing, the measuring and plotting of the traverse on the paper are done simultaneously. The plane table equipment is set up at every traverse station one by one in a clockwise or anti-clockwise direction. The sides of each traverse station are drawn on paper to a suitable scale. If there is any closing error, graphical methods are used for its adjustment. Now, a traverse station is a geodetic point whose position on the Earth's surface within a given system of coordinates is determined by the method of traversing. It may be stabilized by a large concrete monument set into the ground or by a geodetic beacon erected on the surface. In a traverse, 3 stations are considered to be of immediate significance. These stations are the rear, the occupied, and the forward. The rear station is the station that the surveyors who are performing the traverse have just moved from, or it is a point to which the azimuth is known. The occupied station is the station at which the party is located and over which the instrument is set. The forward station is the immediate destination of the party or the next station in succession. In surveying, Traverse is defined as the field operation of measuring the lengths and directions of a series of straight lines connecting a series of points on the Earth. Each of these straight lines is called a traverse leg, and each point is called a traverse station. Traverse legs are measured by using electronic devices, a 30-meter steel tape, or trig traverse procedures. These measurements are used to compute the relative horizontal position of each unknown traverse station on some system of coordinates, such as the UTM grid system.
Hi everyone, I am Riegil Kae T and I will be discussing the types of compass surveys. The first type of a compass survey is an open compass traverse. It consists of a series of lines expanding in the same direction. A traverse is said to be an open traverse when the traverse starts at one point and terminates at another point. It is also called an enclosed traverse. Here, the figure shows that the product of an open compass traverse is always a polyline. The corners of the line may represent points whose positions it is wished to plot, or the polyline may describe the shape of a linear feature. This type of a compass survey is the least desirable traverse type because it does not provide the opportunity for checking the accuracy of the fieldwork. All measurements must be carefully collected and every procedure for checking position and direction must be used. Therefore, the planning of a traverse should always provide for closure of the traverse. Now let's proceed to its suitability. The open compass traverse is suitable for surveying a long narrow strip of land such as the pathway of a highway, railway, pipeline, coastline, and transmission line. The second type of a compass survey is a closed compass traverse. A traverse is said to be a closed traverse when the traverse returns to the starting point, thereby forming a closed polygon. It can either begin or end on the same point, or begin and end at points with previously determined and verified coordinates. The product of a closed compass traverse is always a polygon. The corners of the polygon may represent points whose positions it is wished to plot, or the polygon may enclose a landscape feature, as it does in the example below. Now for its suitability, the closed compass traverse is suitable for surveying the boundaries of ponds, sports grounds, forests, and survey for large areas which tie lines cannot be measured for area determination and control for mapping. Now let's proceed to the summary of the procedure for adjusting a closed compass traverse. Here is the summarization for the adjustment of a closed compass traverse. First is to sketch the closed compass traverse using the observed forward and backward bearings. Second is to compute each of the observed interior angles. Next, compare the sum of the computed observed interior angles versus the theoretical sum of the interior angles. Then solve for the discrepancy, correction, and the MPVs, or the most probable values of the interior angles. After having the MPVs of the interior angle, adjust each of the forward and backward bearing based on the best line considered and the MPVs of the interior angles. By this time, the forward and backward bearing shall be equal numerically, retaining its original direction. You can check your solution by doing the same process of adjustment to the best line, and if the answer is the same as the forward and backward bearing which you consider the best, your computations are all correct. After that, put all your output in a tabular form.
So now we are gonna be talking about the latitude and departure. Latitude. Latitude of any line. The latitude of a line is its projection on the north-south meridian and is equal to the length of the line times the cosine of its bearing. The latitude is the y component of the line, which is also known as northing or southing. Latitudes of line with northerly bearing are designated as being north or positive. Those in a southerly direction are designated as south or negative. Departure. Departure of a line is its projection on the east-west meridian and is equal to the length of the line times the sine of its bearing. The departure is the x component of the line, which is also known as easting or westing. Departures of lines with easterly bearings are designated as being east or positive. Those in a westerly direction are designated as west or negative. When you say y component, it represents the latitude, while the x component represents the departure. On the right figure, the line AB has its latitude AC and departure BC. The angle theta is the bearing of the line AB. For the computation of latitude and departure, the formula is latitude equals the distance times cosine theta, while departure equals distance times sine theta. Figure 1 shows the correct sign convention for latitude and departure. In the first quadrant, the latitude and departure are both positive. On the second quadrant, the latitude is positive and the departure is negative. On the third quadrant, the latitude and departure are both negative. And lastly, the fourth quadrant is that the latitude is negative while the departure is positive. Error of closure. An error of closure is a short line of unknown length and direction connecting the initial and final station of the traverse. It is approximately determined by plotting traverse to scale, or more exactly, by computing hypotenuse of a right triangle, whose sides are the closure in latitude and closure in departure respectively. In any closed traverse, there is always an error. No survey is geometrically perfect until adjustments are made. For a closed traverse, the sum of the north and south latitude should always be 0. The formula for the error of closure. The error of closure equals the square root of error of latitude square plus error of departure square. The formula for position or relative error equals error of closure over the perimeter of all courses, where EL equals to closure in latitude or the algebraic sum of north and south latitude. ED equals to closure in departure or the algebraic sum of east and west departure. So here is an example. Parcel of land has been surveyed in the field and the length of bearings of the various sides are shown. From the table, it shows the different line with corresponding bearing and distances. Line AB has 53 degrees 27 minutes, is of north with a distance of 59.82 meters. Line BC has 66 degrees 54 minutes, is of south with a distance of 70.38 meters. Line CD has 29 degrees 8 minutes, is of south with a distance of 76.62 meters, while line DA has 52 degrees 0 minutes, is of north with a distance of 95.75 meters. The first question is compute the error of closure for the traverse shown, and the second question is what is the precision of the linear measure of the traverse. The first step is to solve the latitude and departure. The line AB lies in the first quadrant, and so the latitude and departure are both positive. The latitude of line AB equals 59.82 times cosine 58 degrees 27 minutes is equals to positive 35.62 meters. the departure of line AB equals to 59.82 meters times sine 53 degrees 27 minutes equals to positive 48.06 meters. The line BC lies in the fourth quadrant, and so the latitude and departure are on opposite side. Latitude BC equals 70.38 times cosine 65 degrees 54 minutes is equals to negative 27.61 m. The departure of line BC equals 70.38 times sine 65 degrees 54 minutes is equals to positive 64.74 m. The line CD lies in the third quadrant, and so the latitude and departure are both negative. The latitude of line CD equals 76.62 times cosine 29 degrees 8 minutes is equals to negative 66.93 m. The departure of line CD equals to 76.62 meters times sine 29 degrees 8 minutes equals to negative 37.30 m. The line DA lies in the second quadrant, and so the latitude and departure are on opposite side. The latitude DA equals 95.75 times cosine 52 degrees 0 minute is equals to positive 58.95 m. The departure of line DA equals 95.75 times sine 52 degrees 0 minute is equal to negative 75.45 m. Next step is to get the sum of the value of latitude and departure. So positive 35.62 plus negative 27.61 plus negative 66.93 plus positive 58.95 is equals to positive 0.03 latitude. So remember from the last slide, it says that the sum of the north and south latitude should always be 0. So the answer here is 0.03 latitude. While positive 48.06 plus positive 64.74 plus negative 37.30 plus negative 75.45 is equals to 0.05 departure. So the next step is to input the summation of latitude and departure. Error of closure equals square root of error of latitude 0.03 square plus error of departure 0.05 square equals to 0.0583095185 rounded off to 4 decimals equals to 0.0583. Step 4 is to solve the parameter. Parameter equals 59.82 plus 70.38 plus 76.62 plus 95.75 is equals to 302.57 m. Next step is to input the parameter to the formula of the precision. So remember, the formula for the precision or relative error equals error of closure over the perimeter of all courses. So precision equals to 0.0583 over 300.57 is equals to 1 over 5,190. So the next topic would be balancing a survey. In balancing a survey, there are two common methods in balancing a survey. So the first rule is the compass rule. The correction to be applied to the latitude or departure of any course is to the total correction in latitude or departure as the length of the course is to the length of the traverse. The compass rule is used when it is assumed that the closing errors are as much a result of errors in observed angles as of errors in measured distances. The second method is the transit rule. The correction to be applied to the latitude departure of any course is to the total correction in latitude and departure as the latitude or departure of that course is to the arithmetic sum of all latitude or departures in the traverse without regards to sign. The transit rule is used when it is assumed that the closing errors are caused less by errors in the observed angles than by the errors in the measured distances. For the formula of the compass rule for latitude, we have correction of latitude of any line is equal to the length of that line over the perimeter of the traverse times error in latitude. For departure, we have correction of departure of any line is equal to the latitude of that line over the perimeter of the traverse times the error of departure. For the formula of the transit rule, for the latitude, we have the correction of latitude of any line is equal to the latitude of that line over the arithmetic sum of all the latitude times the error of latitude. For departure, we have correction of departure of any line is equal to latitude of that line over arithmetic sum of all departure times the error of departure. For the table shown, we are going to use the previous example for this topic. In this example, when you solve the summation of latitude and departure, there is a little error. So when you got an error, you have to balance the latitude and departure using the transit rule or the compass rule. So for this example, we are going to be using the transit rule to balance the latitude and departure. In our problem, we have already the following. Error of latitude is equal to 0.03. Error of departure is equal to 0.05. Total latitude is 189.11, while the total for departure is 225.55. The latitude of line AB. Correction of latitude is equal to 35.62 over 189.11 times 0.03 is equal to 0.006. The departure of line. Correction of departure is equal to 48.06 over 225.55 times 0.05 is equal to 0.011. The latitude of line BC. Correction of latitude is equal to 27.61 over 189.11 times 0.03 is equal to 0.004. The departure of line BC. Correction of departure is equal to 64.74 over 225.55 times 0.05 is equal to 0.014. The latitude of line CD. Correction of latitude is equal to 66.93 over 189.11 times 0.03 is equal to 0.011. The departure of line CD. Correction of departure is equal to 37.30 over 225.55 times 0.05 is equal to 0.008. The latitude of line DA is equal to 58.95 over 189.11 times 0.03 is equal to 0.006. The departure of line DA. Correction of departure is equal to 75.45 over 225.55 times 0.05 is equal to 0.016. So we now already computed the corrections of each line of the latitude and departure. Now we are going to compute the new value of the latitude and departure. We should always remember that when the error is positive, the correction will be negative and vice versa. For the latitude of line AB, 35.62 minus 0.006 is equal to 35.61. For the departure of line AB, 48.06 minus 0.011 is equal to 48.05. For the latitude of line BC, negative 27.61 minus 0.004 is equal to negative 27.64. For the departure of line BC, 64.74 minus 0.014 is equal to 64.73. For the latitude of line CD, negative 66.93 minus 0.011 is equal to negative 66.94. For the departure of line CD, negative 37.30 minus 0.008 is equal to negative 37.31. For the latitude of line DA, 58.95 minus 0.009 is equal to 58.94. For the departure of line DA, negative 75.45 minus 0.016 is equal to negative 75.47. We now have corrected the value of latitude and departure of each line. We will now check if we have balanced the latitude and departure. The first is to get the summation of latitude by adding all the corrected values. After adding all the corrected values, we get the answer 0, which means that we have already balanced the latitude. Now, we will balance the departure. After adding all the corrected values in the departure, we get the answer 0, which also means that we have the balanced departure.
The next topic is the computation of area, which will be discussed by me, Rene Bacay, and Vinz Bacay. The first method of computing for the area is by triangle method. The figure on the right shows that a tract can be divided into simple geometric figures such as triangles, rectangles, or trapezoids. The sides and angles can be observed and their individual areas calculated or totaled. This is the formula to be used for triangle method. To find the area of each individual triangle, area is equals A times B times sine C all over 2, where C is the included angle between side A and side B. To give an example, we solve for the area of the figure using triangle method. The first area we will find is the triangle on the left, where side A1 is equals to 65, side B1 is equals to 50, and angle C1 is equals to 110 degrees. The second area, which is the middle triangle, is where side A2 is equals to 95, side B2 is equals to 50, and angle C2 is equals to 50 degrees. The last triangle, which is on the right, is where side A3 is equals to 70, side B3 is equals to 60, and angle C3 is equals to 60 degrees. So once we input these values to the formula given, we get area 1, which is 1,527 square feet, area 2, which is 1,819.36 square feet, and area 3, which is 1,818.65 square feet. That gives us the total area, which is 5,165.01 square feet. The second method is area by coordinates. Coordinates is the most frequently used method when computing the area within a closed polygon. As shown on the figure on the right, coordinates of each angle point must be known. This is the formula we will use to find the area using coordinates. It looks confusing at first, but on the next slide, I will show you another way of writing it down so that you could have a better understanding of the formula seen in this slide. This is the other way of expressing the formula of the previous slide. First, we get the sum of the factors of the arrows in blue. So those are the factors of XA and YB, etc. Then we subtract that with the sum of the factors of the arrows in red, which are the factors of YA and XB, etc. Then we divide that by 2, which will give us the area. So we have here an example for solving for the area using coordinates. We can see here points with their respective x and y coordinates. So we have point A is on 0 and 169.02. Point B is on 30.55 and 29.94. Point C is on 226.02 and 0. Point D is on 139.37 and 152.26. Lastly, point E is on 159.97 and 340.65. We input the values to the formula given on the previous slide, and we get 0 times 29.94 plus 30.55 times 0 plus 226.02 times 152.26 plus 139.37 times 340.65 plus 159.97 times 169.02 minus 30.55 times 169.02 minus 226.02 times 29.94 minus 139.37 times 0 minus 159.97 times 152.26 minus 0 times 340.65. After summing it up we get 108,928.3251 minus 36,287.632, which is equals to 72,640.6931. We divide both sides by 2. We get an area of 36,320.45 square feet.
We will now proceed to the third method to compute for the area, which is area by double meridian distance. So what is a double meridian distance? It is a traditional method of computing the area of a closed polygonal traverse. So we have a few rules to remember when doing this specific method. First, the double meridian distance or DMD of the first course or line is the departure of the course itself. Next, the DMD of the succeeding course is equal to the DMD of the previous course plus the departure of the previous course and the departure of the course itself. And last but not the least, the DMD of the last course is the departure of the course itself but opposite in sign. So here is the formula in getting the area in the double meridian distance method. Area is equal to 1/2 the summation of the product of the double meridian distance and the latitude. To understand this method better, we will now discuss an example for the DMD method. The example states that we have to find the area of the closed traverse below using the DMD method. All units are in meters. So we have 4 lines, line AB, BC, CD, and DA. Line AB has a latitude of negative 18.63 meters and a departure of negative 11.77 meters. Line BC has a latitude of positive 8.03 and a departure of negative 5.96. The rest of the latitudes and departures for each line follow. So, remembering the rules in the DMD method, we can see that the first rule states that the DMD of the first course is the departure itself. So, the DMD for line AB is its departure, which is negative 11.77. The DMD of the next line is equal to the DMD of the previous line plus the departure of the previous line and the departure of the line itself. So, to get the DMD of line BC, we will add negative 11.77, which is the DMD of the previous line, plus negative 11.77, which is the departure of the previous line, plus negative 5.96, which is the departure of line BC itself. Adding these 3 values will give us negative 29.50, which is the DMD for line BC. To get the DMD for line CD, we still follow the same rule. We will add the DMD of the previous line, which is negative 29.50, plus the departure of the previous line, negative 5.96, plus the departure of the line itself, negative 1.36. Adding these values will result to negative 36.82 for the DMD of line CD. For the last line, the DMD is simply the departure of the line itself, but opposite in sign. This is stated in the third rule for the DMD method. Since the departure for the last line is positive 19.09, then it follows that the DMD is negative 19.09. To get the double area, we simply multiply the DMD and latitude of each line. So for example, for line AB, the DMD negative 11.77 multiplied by the latitude negative 18.63 will equate to 219.2751. The same process follows for the double area of the next lines. Now, to get the area, we need to have the summation or total of the DMD multiplied by the latitude. The product of these two can also be called the double area. So the sum of the double areas of all the lines is negative 305.2452. Now that we have this summation, we will now apply it to the formula for area, which is 1/2 the summation of the product of DMD multiplied by the latitude. So, substituting the values, we have negative 305.2452 divided by 2 is equal to negative 152.6226 square meters. Since there is no negative area, then the negative sign will be disregarded. Therefore, the final answer for the area is 152.62 square meters. The last method in calculating the area is through the double parallel distance method. Parallel distances can also be computed in a manner similar to meridian distances by using the latitudes of the successive courses instead of departures. The same rules apply for the DPD method, but we will use latitudes instead. First, the double parallel distance or DPD of the first course is the latitude of the course itself. Next, the DPD of the succeeding course is equal to the DPD of the previous course plus the latitude of the previous course and the latitude of the course itself. And last but not the least, the DPD of the last course is the latitude of the course itself but opposite in sign. So here is the formula for the area for the double parallel distance method. Area is equal to 1/2 the summation of the product of the DPD and the departure. So we can really observe here that the DPD method is quite similar to the DMD method. Again, the only difference between the two is the use of the latitude and departure. We will now proceed to this example to understand the method better. So find the area of the same closed traverse below, but this time using the DPD method. All units are in meters. This table is exactly the same as the previous example, but we will be using the DPD method instead of the DMD method. So we still have the same given values for all the latitudes and departures for each line. Now, to get the DPD of the first line, we remember the first rule in DPD method, which states that the DPD of the first course is the latitude of the course itself. So the latitude of line AB is negative 18.63, so that is our DPD as well. Next, for the succeeding course, the DPD is the sum of the previous DPD, the previous latitude, and the latitude of the course itself. So for line BC, we have negative 18.63 plus negative 18.63 plus 8.03. The sum is equal to negative 29.23, which is the DPD of line BC. We also follow that rule for line CD. So the DPD of the previous course, negative 29.23, plus the latitude of the previous course, positive 8.03, plus the latitude of the course itself, positive 4.81, will give us the sum of 16.39, which is the DPD for line CD. For the last line, the DPD is simply the latitude of the same course but opposite in sign. So since the latitude is positive 5.79, then the DPD is negative 5.79 for line DA. This is stated in the third rule in the DPD method. The double area is computed by multiplying the DPD and the departure. For example, for line AB, we multiply negative 18.63, which is the DPD, and negative 11.77, which is the departure, to get the answer of 219.2751. So now, to get the area, we have the summation of the product of the DPD and the departure, which is positive 305.2452. Substituting that value to the formula, we have 305.2452 divided by 2 to get the answer of 152.6226 square meters. Following two decimal places, our final answer for the area of the closed traverse is 152.62 square meters. This answer is exactly the same to the area that we computed for the DMD method before. Whether you use the DPD or DMD method, the value of the area for the same problem will be the same as well. So that is all for our report for Unit 4 in surveying, and we hope you learned something new. Thank you for listening.